Okay, welcome back to another memory shortcut video. Today will be on reactivity series. Okay, so I'll go through a few memory shortcuts and analogies for a few concepts in reactivity series. Okay, let's start with the reactivity series itself. Please stop calling me a cool zebra. I like happy cute head. Okay, so this is how you remember the reactivity series. Your teacher might give you their own memory shortcut and you can use that as well. Okay, so potassium, sodium, calcium, magnesium. Then you have carbon, zinc, iron, lead, hydrogen, copper, and silver. Okay, so please stop calling me cool zebra. I like happy cute N. So at the top, potassium, we have the most reactive metal. Okay, then at the bottom, silver, we have the least reactive metal. So this is like a ranking system from most reactive to least reactive. Okay, then in the middle, we have carbon and hydrogen. Even though these two are not metals, they are in the reactivity series so that they can be used to compare the reactivity with other metals. Next, moving on to displacement reactions of metals or oxide compounds. So let me tell you a workplace manager analogy. In a small office, right, there was this manager named Tom. Okay, even though he had the title of a manager for many years, he struggled with things like decision making, missed deadlines, and he also didn't have the skills to lead effectively. And then on the other hand, right, there was an employee named Jerry. Okay, even though Jerry joined the company only 2 months ago, he was much more competent. He could solve problems quickly, he could communicate well, and he basically got the respect of the whole team. The CEO noticed that the department wasn't performing as it should, okay, and decided that a change was needed. So in the end, he promoted Jerry to the managerial position. That means now Jerry is the manager and Tom became a normal employee. So Jerry replaced Tom's position to become the new manager. So how do we lead this to displacement? The more reactive metal will displace a less reactive metal from its compound. Okay, just like how the more competent person, Jerry, replaced Tom, which is less competent, from the managerial position. Okay, then in chemistry terms, for example, magnesium can displace copper from copper 2 sulfate because magnesium is more reactive than copper, okay, to form magnesium sulfate and copper. So that is displacement reactions. You can use this analogy to help you understand. Okay, next, moving on to thermal effect on carbonates. Let me give you a fridge magnet analogy. So think of the magnets on your fridge at home, right? You have some strong magnets, you have some weak magnets. Then the stronger magnets are more strongly attracted to the fridge, right? And the weaker magnets are, of course, less strongly attracted. So it is, of course, harder to remove the stronger magnets from the fridge compared to the weaker magnets. So this is the same for carbonates, metal carbonates. The metal carbonate containing the more reactive metal will have a stronger resistance to decompose upon heating. That means when you try to heat a metal carbonate with a reactive metal, right, it's very hard to remove the metal from the carbonate, so it has a stronger resistance. That's why we can say it's more heat stable. For example, magnesium carbonate is more heat stable than copper 2 carbonate. Okay, this is because magnesium is more reactive than copper. Okay, then actually your more reactive metals, they have a higher tendency to lose electrons and become positive ions. Okay, they have a higher tendency to become positive ions. So magnesium carbonate is more likely to remain as a positive ion inside the metal carbonate, magnesium carbonate. Okay, that's why it has a greater resistance to decompose upon heating and is more heat stable compared to copper 2 carbonate, okay, which contains copper that is less reactive. All right, next, conditions for rusting. Okay, so the memory shortcut is WOW, water, oxygen, and worse if salt or acidic conditions. So there's only two conditions needed for rusting, which is water and oxygen. As long as it comes into contact with iron, iron can rust. Okay, the last one is worse if salt or acidic conditions. That means iron will rust faster if there is salt condition, there's a salt solution, or there is acidic solution. But the main two conditions is water and oxygen. And next, prevention of rusting. First, we have barrier methods. Then second, we have sacrificial protection. So barrier methods, how does it work? Let me give you an analogy. So Iron, right, who is a brave soldier, he faced relentless enemies. So the enemies are water and oxygen. Okay. So iron doesn't want to come into contact with water and oxygen because it will rust. It doesn't want to rust. So to stay safe, he wore armor. Okay, he wore armor to protect him. So it's like a barrier, which shielded him from the attacks. But the armor didn't last forever. Once it wore off, right, iron was left vulnerable and the enemies could strike. Right, the water and oxygen could come into contact with iron. So what does barrier metals do? Barrier metals, they protect iron temporarily. Okay, but once the barrier wears off, they need maintenance to continue to prevent rusting. So that is how barrier methods work. Then for sacrificial protection, this is part 2 of the soldier analogy. Iron, right, who is the brave soldier, continues to be attacked by his enemies, water and oxygen. And just when it seemed iron might fall, a stronger soldier, who is calcium, stepped forward. Based on the reactivity series, calcium is actually more reactive than iron. So calcium is the one that faced the full force of the enemy's attack, and he sacrificed himself to keep iron safe. So while calcium corroded and sacrificed itself, iron stood strong and unharmed. What does this show? Sacrificial protection works by letting a more reactive metal corrode in place of iron. Okay, why? Because the more reactive metal, they have a higher tendency to lose electrons, to form positive ions. Okay, so losing electrons is the same as oxidizing. So calcium will oxidize more readily and will corrode in place of iron. Okay, that's why the more reactive metal corroding in place of iron is called sacrificial protection. All right, that is the end of the memory shortcuts. So it's quite a short video, but I hope it benefited you guys. If you want to get this PDF, right, you can join the Telegram channel below in the description. Okay, it's totally free.